Welcome back, humans and robots alike. Today we'll be talking about mapping and few other components of SLAMs, which are usually useful whenever you are running a real-time and a real-world system. So yeah, let's just jump into figuring out. So before we switch to mapping, I think it's good to first just have a bit of an understanding how measurement works and what measurement are you really taking from sensors, especially sensors like LiDARs or 3D sensors as well, right? So let's talk about LiDARs first. Be it 2D or a 3D LiDAR, it will usually have a beam, and that beam would be emitted. And then when it comes back from that emission, the time delay, along with the range, I mean speed of light, would help you figuring out what the range of that particular reflection back is. So what you see on the bottom is a 3D LiDAR. It's spinning quite fast, I might add, and it also has this laser, which you can see that's being the camera gets exposed to that light quite a bit. And so this is basically Livox Mid 360 LiDAR. It's a very small, tiny size LiDAR. Uh, and this is basically what I'm trying to demonstrate here is uh, given this light emission and the coming back, also it will remember where at what angle the light came back from. That will give me the bearing. So if you remember the EK slides, we were taking both two things, range and bearing. So those two things are calculated by the LiDAR and given to me as a data ready to go. I don't have to calculate all this. Again, repeating, I don't have to calculate all this. Bearing, range, all this is packed neatly into a particular message for me. If you're using ROS, you will be using laser sensor measurement models, or you can use point clouds, 2D point clouds or 3D point clouds, and then you just directly work off that. Now, to give an understanding how this data looks like, what I have in front of you is a point cloud accumulated over a period of time using a 3D LiDAR. That accumulation point is very important here because with just one scan, you might not see such detailed output coming in. And the way you can observe that is it takes it a bit of a time. So once I sit on a seat, it takes it a bit of a time to accumulate and then show me. And also another thing you can see is you can see my beard and other facial features. That's because it also, so other than just range and bearing, it also gives me the intensity. Different materials absorb light in different ways. That intensity is also captured when the reflection comes back to the sensor. So something like a number plate would be highly reflective versus something like a charcoal or a black road would have a lower reflection compared to other things. But it's obviously not enough for you to take this empirical understanding and try to just segment objects just by the way of intensity because it's highly it depends highly upon what the environment conditions are and other things. But yes, in general, the intensity map you build from a LiDAR scan that could give you a good pictorial understanding of how the environment looks like at any point of time using the LiDAR. So let's now talk about mapping, right? So what are we, I mean, initially, what do we map of the surrounding? Because usually till now, mapping has been used to do this thing called as sense and avoid, right? You build this map and then you want to know where these obstacles are. You want to just avoid these obstacles, go in the direction where you should not get any hamperment to your motion. And that's what you would usually do. And because that had been the case, it's changing now quite a bit. So maybe this mapping I mean, from SLAM perspective, I would still say this is accurate enough for what the SLAM would end up being used for. But nowadays, a lot of mapping also has to happen in terms of capturing the RGB modality and other things of the environment because we want to do more of a semantic understanding of the environment. But let's leave that into a bag because it's not coming into play. For now, we know that a map to be generated is to be used for sense and avoid functionality, which has been talked about in different lectures, right? So the occupancy mapping, the challenge or the problem statement which we have with us is given set of poses, given set of observation during those poses, correlated observation with correlated poses, I need to make a map, right? So this probability which you see on the bottom left, I mean side left, is the thing which we want to calculate, right? And how would it look like? It should look like something like this. This is aerospace department at ISC. You can see how it looks, and this is the top view of it. It looks kind of like a plane. I would encourage you guys to go check Google Maps and see how aerospace department looks from the satellite. You'll see it looks something similar to this. Right. So before we go to something like this, let's first understand a bit of math behind how things are happening. Now, in as we did with the other EKF and the factor graph SLAM, we'll assume our world to be 2D. This 2D world will discretize it into occupancy grid, right? So each grid cell would either be occupied or free, or there is another variable which I have not really mentioned here, which is unknown, right? And we will see how that plays a role a bit later. But mainly we are concerned with, is it occupied? Is it free? Is it occupied? Is it free? That's all. And now the problem is the maps are huge. So if you put a conditional dependency of a map with all the nearby cells, it will make things hard, right? It'll make things computationally quite hard. So what you do is you make an approximation like how we're doing for other things. Make an approximation that cells are independent of each other in this occupancy period. Cell at 1 comma 1 does not depend what the cell 2 comma 2 is doing. Is it a good assumption approximation? Probably not. Is it okay for us for now for the task which we have? Yes, right? But yes, of course, you also sometimes want to capture the structural information. So you want to consider how the nearby cells are doing. You do want to do that, but in our use case, in the simple mapping technique, we'll assume that to not be the case. So now we have approximated each cell is distinct. So I just need to, multiply these cells up and then I can get a really good reading out of it or a really good map out of it. So before I do that, let's now think from a little bit different perspective. The probability that a cell is filled or not, given a particular observation, using Bayes' theorem again here, I will uh, avoid. So, I mean, using Bayes' theorem, I will expand this and then also the above this term, because I know that my current observation does not depend on my previous observation. It only depends on my current state. I can reduce this just into this term. Simplify things here. I mean, I keep simplifying things here. And then this zt conditional to x, I use Bayes' theorem again. This is what I would get, and this is what we will start working with now. One thing we want to do is we want to calculate odds. Instead of just calculating probability, we want to calculate odds. So what odds basically mean is, given 200 tries, or let's say given 10 tries, how many in this 10 tries would I get a free cell or a filled cell, right? That is the odds which you're talking about. So P upon 1 by P. So when we try to do that, what happens is the Z term will get cancelled out, right? Px and P bar, that's good for us, right? So this is what we would end up getting as an output of this whole uh, operation. Now to this, because it's a small value, we would like to use logs here so that we can reduce our numerical error towards other steps. So when we do that, we finally get this particular equation. So what it says is my new occupancy value depends upon my old occupancy value minus the log odds of my initialization, occupancy initialization. So initially I will make an assumption, right? I'll make an assumption of whether my cells are occupied, how many cells would be occupied and how many cells wouldn't be. Usually we'll keep this 0.5, that term just goes away, but like this just an assumption, right? And then also you have the inverse sensor model. Given a particular observation, what is the with what how much probability I can say that this was my state. That is the inverse sensor model. Inverse sensor model again is built using what we talked about here, this measurement model which you were trying to build. So yeah, now what it ends up doing is, so on the left side you can see the robot and the environment that robot is in. Also the observation, right? So the blue line is your laser, and on the right side I'm building that log odds heat map. So let me just play this. You can see that when I saw this, okay, let me just let it finish. So I want you to observe few things, right? When it saw a particular obstacle here and a particular obstacle here, and then it finally saw an obstacle here. Now, obviously, if we're seeing an obstacle here and we're using a laser rangefinder, these two places would be free now, right? So it goes from black to, it'll slowly start going from that black box to more of a gray box, and slowly start going towards a free state. So that updation, or that really depends upon my sensor model and the previous reading which I had. So it's a more of an iterative fashion, right? So even mapping, just like how we had other SLAM and other things, it's a lot iterative in nature. So let me replay this again, and make sure you check the left, the observation which you mean the laser observation you see on the top left as well. There also we see an erroneous reading and then we see a good reading. Yeah, we see that the cell was occupied and then it became white. I mean, I would not really say it's an erroneous, it's just that maybe the environment changed or something else happened, right? So that's the gist of this whole mapping part of our 2D SLAM map. And similar to this, you also in 3D space also you can do similar things, but there are a lot more optimization you can do in the 3D space because again you have to. So you can go with this voxel method, or you'll use some other methods in 3D to build the 3D maps. Again, it's a little bit out of course for us for this set of lectures. So you guys can still go and read online how those maps are built. Right. So the overall SLAM structure, right? If I have to put it into words and in a diagram fashion, I'll make it into two sections, right? And also, like I've connected the SLAM to a bigger overall picture. We'll look into it. But for now, let's just consider this blue box. So one is this backend and one is this front end, right? So what backend does is all that factor graph and the EK stuff which we saw, all that is SLAM backend. It's doing optimization for my poses. Second part is my odometry, loop closure, and things like that. So odometry is nothing but, oh, given my IMU reading, I'm either using strap-down navigation or some other method. I am trying to estimate my motions, right? Or maybe I'm also taking into consideration my input control signal and other things. I will consider, I mean, I have to predict my odometry motion. So that is my odometry in the SLAM front end. And in loop closure, what I have is, so basically, let's say you are going around, let me just open up a pen. So you go here, you go right, you come back, and then you come back to the same point, which is great if you had a really good odometry. But more often than not, if you are just using some sort of estimation method, what you would end up seeing is something like this. Did you end up at the right place, same place? No. But is there a way to improve this? So you know that this point, I mean, you can detect that this point and this point are the same. And because you're using factor graphs, and you're going to, optimize over the whole graph. This is not a EKF graph being or EKF slam being used. What you could actually do is you can use uh, loop closure to help you come to the same point again. And so that helps you to do drift corrections, and which is really good and really important. And so, yeah, so that basically encapsulates the SLAM stuff. Another thing which I want to talk about is usually you will use like SLAM with a global planner, local planner, and that will give an input to your robot and environment. So usually for a global planner, you would want to use an output coming from SLAM backend. And for my local planner, because I just need like bit of my surrounding, I don't need an overall picture. Just the SLAM front end output can be sufficient enough for you to work on it. So this is how you would, structure different outputs coming from different systems because backend will take some time. And this, if this takes time for the local planner, that's not good. But for global runner, 1 second also it's fine. I can still it's still doable to use that. And front end will obviously work at a higher hertz, so this really works out in our favor, right? And let me just clear this up. What it does is it gives you something, some sort of a system like this. So this is a robot in lab. It's called Volta. It has a 2D LiDAR in front. On the left side of the picture, you can see the 2D LiDAR. So it has both the observation and the map being built. Red is that laser scan. So laser scan is not really, uh, it's the direct and whatever the reading you get, it's just that. So the poses are not being correct. So it's not properly going to overlap with your map here in this picture. And you see there were two obstacles and it's, nicely avoiding those two obstacles and going around it. So the end point was given on the other side of the obstacles, right? Let me just do that. Let it do that. Oh, so by the way, this is using a very simple bug algorithm, and it's just taking into consideration the input which we had from that map. Now you can use bug algorithm. So bug algorithm in this case is not really utilizing map as such, but another thing which you could try using is you can use DWA or some other advanced methods, and that will help you get a better uh, obstacle avoidance into play. Also, so this is using Hector's lab to build this map, right? Okay. So as I talked about, odometry will take in LiDAR or a visual reading. It could also take inertial. So pre-integration you can do using Lie algebra. And then you can take maybe radar odometry or even leg odometry. So if you have a legged robot, you can take a legged odometry. Or if you have a wheel odometry also, you can use that. Okay. So this is again a small demonstration of how the mapping. You can see the poses it has. It's a building basically a map of a lab. What you can see here are these are like small cubicles which we have, and those are all like nicely getting mapped. So in the previous, you didn't see the proper map being built, but I just wanted to show what a proper map looks like in a 2D world, right? And so yeah, so again, coming back to this thing called as loop closure, what you need to do is it's two-step process, right? You need to recognize that place. Is it the old place? Is it the old place? You need to keep doing that. You can use bag of words or scan context or anything to do that. And then also you need to do this post estimation. So you need to register. You need to register your current position with a match and then do a loop closure in your factor graph and then use that as an output. So this is what it would look like. So you can observe that there are these yellow lines, right? I hope it is visible. So these yellow lines are the factor graphs or the loop closure stuff which is happening because it's a 3D LiDAR, even if it's a bit away from that particular same location, especially on corners, you'll still be able to see a good part of common space. And so this is where we started, and now you can see a lot of yellow lines come into play because a lot of loop closure factors would happen. So blue is my current odometry, and then the lines, interlinking lines between two blue lines are my loop closure indicators, factor indicators, basically. Great. So again, so just to recap, we have this backend, front end. We do feature extraction, we do preamp integration, also loop closure detection or data association, what you want to call it in front end. In backend, you will do this map correction and that nonlinear optimization we talked about. All right, so that is for this lecture. I will catch up with you guys in the next one. Thank you.